So this is another example for Chapter 15, Section 10, dealing with acid-base properties of salt solutions. In this example, we're given a pH of a salt solution and we're asked to find what our starting concentration of the salt is. So the process is going to be generally the same. We have to figure out what type of salt we are dealing with, acidic, basic, or neutral, and then set up our ICE tables and determine what concentrations we know, what concentrations we need to find. So, first question, what type of salt? So we have K+, which we've already determined is neutral. Then we have CH3, COO-. When this interacts with water, we're going to form acetic acid and OH-, which we know that's a weak acid, so we're in equilibrium. So we're producing OH-, so this is a basic salt. All right. So we want to find what our original concentration is for our salt. So if we kind of think about this in the same process that we did the last one, and that we're going to look at our salt splitting apart into its ions, and then our ion then in equilibrium. So we start off with our salt. When that's dissolved in water, we split apart into K+ and the acetate ion. We have our ICE table for this. Our initial concentration of our salt is what we're looking for, so that's actually our X. And initially we're going to have 0 of each of these. Our change in this case, we still have a strong electrolyte, so this is going to change by completely consuming all of what we start with, so that we have none of our starting salt. Then we have plus X and plus X. So our initial concentration of our acetate ion is going to be our X value. So that's what we put into our next ICE table when we look at the equilibrium of the acetate ion in water. So our initial concentration of our acetate ion is X. We don't care about water. We have no acetic acid and no OH- present in the beginning. Now for our change. Our change has to give us an ending concentration that matches with our pH. So we actually have to figure out what our concentration of OH- is in that solution to cause a pH of 8, and that will tell us what our change is going to be. So we know that our pH is equal to 8. So our POH is going to be 14 minus 8. So we have 6. And therefore our concentration of OH- is going to be 10 to the negative 6 molar. So that's what we know goes here for our ending concentration. We know that this is 10 to the negative 6. If this is 10 to the negative 6, that means our change was plus 10 to the negative 6. Our change for the acetic acid is the same. Oops, not 16, 6. So our ending concentration of the acetic acid is 10 to the negative 6. Over here, we're subtracting 10 to the negative 6. So we have x minus 10 to the negative 6, which that should just be approximately x. Now we have our ending concentrations. We can use our Kb expression to solve for x. We have to use Kb and not Ka because we're producing a base here. So our Kb is going to be equal to our acetic acid times OH minus divided by the acetate ion. And our value for Kb is going to be Kw divided by Ka. So if we plug in some values here, we're going to have 10 to the negative 6 times 10 to the negative 6 divided by x is going to equal 1.0 times 10 to the negative 14. That's our Kw value divided by Ka, which is given. We have 1.8 times 10 to the negative 5. So I get x is equal to 0.0018. We want to check that our approximation is still okay. So we have 10 to the negative 6 divided by our starting concentration, 0.0018 times 100. That's definitely going to be less than 5%, so our approximation is okay. So our x that we've solved for here was our starting concentration of our acetate ion, which then came from our starting concentration of our acid. So our final answer then is our concentration of KCH3COO is equal to 0.0018 molar. All right. One last question for section 15.10. So we've dealt with what happens when we have a strong acid with a weak base or vice versa, but what happens if both of our anions in our salt are both weak? Okay. So in other words, if we look at an example, what type of salt is ammonium cyanide? So if we look at how each of our ions are going to interact with water, we have the NH4 plus with H2O. It's going to lose a proton, act as an acid, so we'll form NH3 and H3O plus. NH3 is a weak acid, so we will be in equilibrium, so we are going to produce H3O plus. We look at Cn minus interacting with water. We've seen this before. It forms HCN and OH minus. HCN is a weak acid, so we are going to be in equilibrium. Oh, I think I called NH3 a weak acid. I meant to call it a weak base, going in the reverse direction. HCN, our weak acid, also going in the reverse direction. So we are producing both an acid and a base. We're producing H3O plus and OH minus. So the question becomes, is this a basic salt or an acidic salt? And what we have to do in order to answer that question is look at our Ka and our Kb values for these. Okay. NH4 is an acid, or NH4 plus is an acid, so we look at Ka for NH4 plus, and this is 5.6 times 10 to the negative 10. We need a Kb value for Cn minus, which if you look it up or calculate it from the Ka of HCN, you get Kb is equal to 2.0 times 10 to the negative 5. So we want to basically look at which equilibrium is going to win, which one is going to more heavily favor the products. So in this case, Kb is greater than Ka. 10 to the negative 5 is larger than 10 to the negative 10. So our second equilibrium here is favoring the products more, meaning we're producing more OH minus. So NH4Cn is a basic salt. So Kb is greater than Ka. So our second equilibrium favors the products more. So we have more OH minus, which makes NH4Cn is a basic salt.